But we'll get started pretty much right in time here. So Maura's going to do a presentation about the Oat Brand study, and then we'll talk about logistic regression. I will get graded homeworks and some comments back on that. Some things have come up in the last couple of days that got in my way of doing things, but we'll get those back to you. We don't meet next week. Wednesday and Friday would be off anyway, but Monday I'll be away. So there's the projects and presentations, which is plenty of things to do, to work on. There will be a final homework on some of the material with categorical data and logistic regression, a couple of problems to look at. I should get that posted shortly. So those would be things to work on. And then we would return to a little more on logistic regression and some things with binomial data there. But without further ado, for this presentation, there it is. Large, okay.
All right, so for our most recent homework, we looked at this high and low fiber diet study that looked at cholesterol. And so I looked into that a little bit more and decided to look more into the study design. We did a lot of computations on that. And so I wanted to look at this a little more closely. So I found the actual published study. In the book, they kind of gave a little bit of a summary of it. So I found the actual study and read that entire piece to gain a little bit more information. So obviously talked a lot more than just the couple paragraph summary in our book. So this is the title of it and then the 4 authors who worked on it. So Oat Brand, some nice pictures of it. That was obviously one of the main things of the study. It wasn't just looking at particularly high and low fiber diets, it was looking particularly at Oat Bran as a soluble fiber. So that was the difference than some other studies that have been conducted. So they looked at a lot of other studies that were looking at fiber in diets related to both cholesterol and blood pressure, but they wanted to examine Oat Bran specifically because of its soluble nature. So serum cholesterol. I also wanted to look at that because I know what cholesterol is, but this serum cholesterol was, I guess, a slight subset of, or I guess it contained more, but this was a definition I found online going into that, looking at the HDL and LDL and the triglycerides found in the blood. So that was the test that they did, was using blood samples to look at this. So this is kind of the study design that we saw in the book. So it was 20 hospital employees, randomized double-blind crossover study. So the subjects didn't know which group that they were in, and they were randomized into those groups, and then halfway through they switched. So they did 1 week of their regular diets before an initial test, 6 weeks of whatever diet they were initially assigned to. So 9 were initially in high fiber and 11 in low fiber. And then they switched diets, did 6 more weeks before a final test. So looking at the study, I learned a little bit more. So there was originally 24 participants, but 3 dropped out, just couldn't do the eating, and then 1 didn't do the final blood test, so they couldn't be included in the study. And what I thought was really interesting is 16 were dietitians. So we knew that they were hospital employees, but I thought that was a really important factor, just because a dietitian knows a little bit more about their diet, and they probably are more health conscious than your average person would be, and know a lot more about nutrition and what they're eating. So also 16 were women and only 4 were men, so there was a pretty big disparity there as well. Had an average age of 30 years old. And then it talked a little bit in the book about some of the requirements. So they could not have high blood pressure. So 150 over 95, I believe, was their highest cutover. Couldn't be taking medicine for blood pressure or serum lipid levels. Couldn't have hyperlipidemia, not sure what that is, but I'm sure there's some sort of test that they can determine that they don't have that or qualify as obese using the BMI measure. And another thing, women were not using oral contraceptives and had to have regular menstrual cycles so that they were in the same place in their cycles when they started each diet. So that was another thing that was controlled in this experiment. So interesting thing about the study design that they made sure to control.
Moving.
There we go. And a little bit more about the meals and some of the differences between them, I guess. So the high fiber meals had about 3 grams more fat than the low fiber meals. So not a huge difference, but potentially could have impacted results. So the muffins had 20 grams of either low fiber or high fiber flour, and the meals had 40 grams, and the participants were told to have 100 grams a day of whatever their supplement was. And then outside of that, they could eat whatever else, and that wasn't recorded. So I thought that was another interesting part of the study that wasn't really controlled for, is that someone on the low fiber diet could have been having lots of high fiber foods outside of their meals. So that could impact the results in the end of this study. So some different types of studies that could have potentially been used. And the study discussed a little bit about why they used their type of study based on ones in the past that hadn't worked out, and they were hoping that theirs had, but these are some other types. So this study, they randomized into groups, gave them foods, and looked at the results. They could have potentially done something where they looked at people's diets, so had them fill out surveys or track their food intakes, and then use that to look at what their cholesterols are measured at to see if there was an impact there. Also, Professor Larson and I talked about this a little bit, so that it was 6 weeks and then 6 weeks back-to-back of the 2 diets. So there could have potentially been some crossover between the 2 diets that could have had an impact where, if you had one, that it just continued over into a few weeks of your second diet. So I'm wondering if that had an impact, if there could have been like a buffer period between the 2 diets, if that would have changed results at all. Talked about potentially if there's just 2 larger groups and they didn't switch diets, what that could have seen. This helped it, I think, in a smaller study was really important because 20 is not a very large group, and 10 in each group. There could have easily been some big differences in the 2 groups that could have impacted the results just because there wasn't a wide sample size. So if you have larger groups, then you could just do 1 each. And then another issue is it only looked at 6 weeks. I think you could see probably maybe different results if you looked more long-term, because obviously cholesterol is something that you care about more long-term than just a 6-week period. You usually don't want to just lower your cholesterol for 6 weeks and then go back to whatever you were at. Usually it's something that people are looking to do long-term. And that was something that this study actually noted, was that these diets weren't really something that people would want to do long-term. Eating a lot of oat bran was not really desirable. The participants found they weren't very enticing meals. So these were diets that would be hard to follow long-term, which I think in terms of reducing cholesterol would be a more important thing than just following it for 6 weeks. So the results, the study looked at both blood pressure and serum cholesterol. So we just looked at serum cholesterol in the book, so there was actually results on both of these. So at each point, blood pressure was also tested. There was found no significant difference between blood pressure on either diets or before these diets. So it seemed that low or high fiber with oat bran, or another low fiber flour, didn't really seem to have an impact on blood pressure, and both diets decreased serum cholesterol, but neither more significantly than the other. They were hoping to find that oat bran would have a bigger effect, but that wasn't really something that was found through this. And then another important thing that they stated in the study was that the diets caused a slight decrease in the subject's dietary intake of saturated fat and cholesterol. So they were intaking less cholesterol during this study because of the meals that they were eating. So that could potentially be a reason why we see that they have lower cholesterol levels and an increase in polyunsaturated fat. And then, so after the study, the participants were asked about it. So like we talked about how these weren't desirable meals to eat, so that was some of the feedback they got. And also 18 out of the 20 of them were able to guess which side they were in. So it was double blind. Probably wasn't the most effective measure of double blind because they couldn't figure out which ones they were in. And I think part of that could potentially be because 16 of them were dietitians and very well versed in this matter of stuff. And my sources. There's some of the things that I found with the study design. Does anyone have any questions about it?
Good. Natalie, thank you for finding that. But yes, I know it was. Do you know if they had 16 women and 4 men? Did they split them in treatment groups so that they would get, 2 of the men would get bio and 2 would
get? They didn't mention that at all. That was something that I wondered about, but that didn't seem to be controlled for at all, or at least they didn't mention that.
Yeah. So, but publishing in the New England Journal of Medicine that's the top journal. Like that and the Lancet out of England.
Yeah.
So they got it in the top journal, but all these concerns.
Yeah.
They're dietitians, they can figure out what they're doing.
Yeah.
Their average age is 30.
So it's very young groups that probably weren't having cholesterol concerns. Anyways, that's the other thing, is they were all at pretty normal cholesterol and blood pressure levels. So wondering, what impact would it have if they were at higher levels? You might have seen a bigger difference because they needed their cholesterol to go down pretty significantly. So.
But some of these, I've seen in other contexts, they do studies just to say, does the drug or the diet change something like cholesterol? But things like blood pressure are stiffness of the arteries, overall health, and things. Those aren't going to change in 6 weeks. Those are going to change in 6 months or a year, maybe.
Yeah.
So.
Yeah, interesting. That was something that they were.
Yeah, that was actually floating around in your blood. Be dealt with more quickly. So, good. Thank you. So, but it's interesting to see that because, studies are reported, and you can see the statistical conclusion, but there's so much more context that can make it interesting. And we do worry about the statistical method, doing it as a crossover design and taking account of the correlations. The people that are high on both, and low or low on both. So there's a definite correlation advantage there in the analysis. But, so it's important to use the right methods, but it's important to get all this other stuff. Right, so interesting to learn more about that background. For that, thank you. So we're going to talk some about logistic regression as a next method. And so we've been looking at, we looked at linear regression and analysis of variance, where we had a linear, quantitative outcome. And now we have the 0-1 outcome, and we've done some things for looking at proportions in 2 groups. So some summaries with that. And so when we do the logistic regression, when we do ordinary regression and say y is a function of some, predictors, I'll just put a couple in there, plus some error, we model this expected value of y as this, and we can say that the errors generally we said were independent and normal and sigma squared, and we looked at time series methods when they might be like that, but the y in this case is quantitative, meaning not just 0, 1, and so any predictions based on x and y, and I can't draw x1, x2, but as x gets smaller, if these are positive, it's going to keep going down, it's going to keep going up. But in logistic regression, now, yi is either 1 or 0. Right? And so if we use a linear model like that, well, let's see, the expected value of y sub I is just going to be the probability for that person. Right? The expected value, if this is a certain probability p sub I, and 1 minus p sub I are the probabilities, and the average value for that person is some proportion, and proportions are between 0 and 1. So one problem with putting 0, 1 data as an outcome in linear regression is the predictions can go, eventually with x going far enough, go outside the 0, 1 range, and that's not going to be so desirable. So we do something else, is we're going to do a function of this mean. Right? We're not going to say the p sub I, the expected value is linear. We're going to transform this into a scale that stretches over the entire range. Right? So we do what's called a link function. This is terminology that's used in not just linear models, but generalized linear models. So in linear regression, the link between the expected value of y is just linear. The beta 0 plus beta 1, x1, and so on, beta 2, x2. It's just a linear link function. In logistic regression, we use the logit link. And the logit link, the g of the probability there is p is the log of p over 1 minus p. So this is a log odds. And then that thing is related to linear. Just to have a couple x's there to illustrate that. Right? And the thing that the logit link does is it takes this proportion that's between 0 and 1, and then p over 1 minus p, it's still positive, but because p can get really small, you can end up dividing by a very small thing, so effectively the range can go up to infinity, and the log takes something, positive numbers down to 0, goes down towards negative infinity. So the logit, sometimes it's the logit of p, the log of p over 1 minus p then is in this range on the whole real line. So as x changes and you move up and down as far as you want, you're still going to get something that is in a range that makes sense there. Now, we're interested in p. Some people would be interested in the logit of p, but we can undo this transformation and express things as p as a function of our x's. It's going to be a nonlinear function, and this is how it goes. So if our g of p, the log of p over 1 minus p, is some number, we call it eta, and then we exponentiate things. Right? That takes out the log, so we get e to that. And then p equals e to the eta times 1 minus p. And then if we put p on both sides, there's a 1 plus e to the eta on this side equals e to the eta. So I've multiplied that, and that's there. And this one's a negative, so I've added it back over in Greek terms. So the inverse transformation is p is it's e to the eta over 1 plus e to the eta. And this number, is back on the scale here. So if this mean value, this transform value, this link function, is a function of the x's, then those go in there. So p in the logistic regression is going to have a beta 0 plus beta 1 x1 plus beta 2 x2 up here, and 1 plus e to the beta 0 plus beta 1 x1 plus beta 2 x2 for all the individuals there. So if we can estimate these coefficients somehow, we could do predictions on the linear scale in terms of this linear function, but we could transform them back to the proportion scale and do predictions there. And so the question becomes, what do you do in terms of how do you get that to happen? Well, we can look at the likelihood or probability function of the data and put it in there and then try to maximize that. Right? So estimation of these, of our betas, we're going to look at the likelihood function. One way to go about doing it. Right? So we have the y sub i's are either 1 or 0, and they had a probability for each of these. Right? And so we're going to have this for all of our subjects. And so our probability that, that all of our y's have all of their datas, all in data points together. If all these are independent of one another, independent individuals, right, then we could write the probability that we get y sub 1 equals y sub 1, y sub 2 equals y sub 2, and so on, as a product of I going from 1 to n. Well, there's a p sub I to the y sub I, and a 1 minus p sub I to the 1 minus y sub I. There's that thing. And that would be the joint likelihood. What we're going to do is express the p's in terms of the betas and see that it's a function of the betas. And the numerical methods are used to maximize that, to find maximum likelihood estimate of the betas. So we can get it closer to the function that we're looking for by taking pi, 1 minus pi, that thing to the yi, and then there's 1 minus pi over here. Right? So the minus yi puts that in the denominator, and I'm just going to group those two terms. And this pi, 1 minus pi, is in the logit. I'll move this over here to get more space. So it's a product of going from 1 to n. So p sub I, so if we would want to take the log of that to get the logit, but we could take the exponent and the log are different functions. So if we do e to, right, so if we do e to the log pi over 1 minus pi, that's just pi over 1 minus pi, right? So this is, thinking about this as natural log, those are just inverses of each other. Right? And so if we do that, we have the pi 1 minus pi to the yi, so that can go out front. So this thing can be written as yi times the log of pi over 1 minus pi. Right? And there's this, I'm just going to leave it as 1 minus pi over here. Right? And so now this logit pi, 1 minus pi, is the function of our betas. This is also the function of our betas. There's another piece on there. So when we put this all together, we get I going from 1 to n, and there's e to the yi, and this logit thing is the beta 0 plus beta 1 x1 I plus beta 2 x2 I there, and this 1 minus this thing. 1 minus p is 1 over 1 plus e to the xi beta, kind of as a function here. Right? So before it had this e to the xi beta up here, and that was p, so 1 minus p is that thing. So we have 1 plus e to the, it would be beta 0 plus beta 1 xi1, x1i plus beta 2 x2i, that thing, and it's all to the negative 1. Right? So we get this function, kind of a complex function there that relates our data to the betas through the probabilities that we see these different things. Right? So some of the y's are going to be 1s, some are going to be 0s, and we're going to get a contribution from every point. And so we use numerical methods. There's not a direct way to find the unique solution that solves this, that maximizes that, but we can use different numerical techniques. There is a maximization technique called, so maximize the function. Right, previous page. And that gives us, beta 0 hat, beta 1 hat, beta 2 hat, or as many betas as there are in our equation, right? This has to be done with numerical methods. The most common one is something called Newton-Raphson. Algorithm. We're not going to go into details of this, but it's kind of interesting. You have this likelihood function. Likelihood functions generally are concave, and so if you pick a starting point, like you get some rough estimate of where you think beta 0, beta 1 would be, you can look at the value of the likelihood at that point. You can look at the first derivative of that likelihood, the second derivative of that, and kind of project where you think the top is. Right? So if it really is quadratic, a quadratic curve there, if the likelihood as a function of the betas, right? The way that those algorithms work, you start with a guess, beta 0 hat. And then you evaluate this and the curvature, and you try to project where you think that top is. And then so you try to adjust these, I'll call it a little t for iterations. You adjust it and you get somewhere close there. It's not exactly a perfect quadratic curve, so you're kind of approximating and it gets close. And then you do it again. So maybe you move over here and you move back a little bit, and eventually you come to a point here that would end up being the maximum likelihood estimate. So kind of interesting numerical things that use first and second derivatives to do that. But the point is we get those estimates there, right? And then we can plug these estimates back in to the logit functions from a couple pages ago, right, to get the linear estimators, or to estimate on the logit scale, or to, if we undo that transformation like we talked about, if you put these estimates in here, that's going to be an estimate of the proportion for each one. Right? And everything's on the 0 to 1 scale where it's supposed to be, and you can test for these different effects. Right? So just like in regression, we can look at hypotheses that some regression coefficient is 0 versus that it's not equal to 0. And just like in regression, we're not going to go into all the formulas, but there's standard errors related to how much data you have and how spread out things are. And so our statistic, we're going to have an estimate. We're going to divide that by an estimated standard error. And under the null hypothesis, right, we will reject the null hypothesis if our z statistic, or its absolute value, is greater than 1.96. We're going to reject it at the 5% level. So there's a z-test that's going to come out for each of our coefficients. So you fit a model with a bunch of them, and you look at one of them, given the other things that are in the model. If it's not a significant predictor, given that what else is in there, you get a p-value and you could reject it. If you don't reject it, you might consider taking that one out because it's not a significant predictor, maybe it's not making that much of a difference in the predictions. You can do confidence intervals say a 95% confidence interval for one of these coefficients in the model, right? There can be a beta hat j plus or minus a normal value, and then standard error from a formula. And we use normals rather than t's there because we're not dealing with normal data. The t distribution things came from normal data. So we can do these tests. There's a little bit different interpretation of what these coefficients mean, right? Because it's linear on one scale, but it's not linear on the probability scale. So what happens what implication does a certain beta have? If you change an x value by one value, we know what it does on the linear scale, right? It changes by, beta j on the linear scale. Well, what does that mean on the probability scale? Right? Or how do you interpret that? Right? So interpretation of coefficients is just a little bit different. So let's just say we have a simpler model to get into this. Beta 0 plus beta 1 x, right? We don't write a error over here. It's not kind of a normal error. But there's that. What happens if we increase x by 1? Plus 1 to x. Then our prediction is log of p over 1 minus p is beta 0 plus beta 1 x plus 1. Right? So on the linear scale, we add beta 1. Right? We're adding beta 1 here. What does that mean on the other scale? Well, if we exponentiate both sides, right, we are, exponentiating. So exponentiate to get this. And so there's going to be e to the beta 0 plus beta 1 x plus 1. So this is the odds. So exponentiating changes the odds this way, right? And so what is that? Well, it's the thing we had before, or would have had before, right? E to the beta 0 plus beta 1 x, right? Times, you can break it out as times beta 1. Right? If you group these things together, you're going to get x plus 1. So this is the change that happens when x changes by 1. It's a multiplicative change on the odds scale. Right? And so the odds of something, if p equals, say, 1/3, then the odds p over 1 minus p is 1/3 over 2/3, which is 1/2. So you're half as likely to succeed as to fail, right? But say beta is 2, right? Or, right, so say beta is, something like 1.5. Say, suppose beta 1 is 1.5. Right? What's that going to do? X goes to x plus 1. And now the odds would be the original odds of 1/2, but if we've changed this, it's e to the 1.5 times that. And what is e to the 1.5? That's a non-trivial number, so 0.5 is 0.5, and that times e to the 1.5 becomes 2.24. That's a big change, right? That's like a 4-fold increase in the odds. So that's pretty big, actually. So this thing goes to 2.24. What type of probabilities create that type of odds? So if we have this thing is our new values of p, right, then 1 minus p prime times 2.4 is my new odds p prime, and 2.24 equals p prime times 1 point. I'm doing that same transformation again, right? But now this is saying p prime is 2.24 over 3.24, right? And that 2.24 over 3.24 is about 0.69. So when you start at a probability of 1/3 and you have a change that multiplies the odds by 2.24, it translates into a probability of 0.69, or more than this is 0.33, about a doubling of the probability. So you have to think about the impacts of coefficients through these transformations to make sense, right? And a coefficient of 0, right, is not multiplying the odds in any way. So it's a little bit different for thinking about that. Anyway, but it gives a way to select models. Pack this thing with extra chairs. When I started teaching, I had to be a graduate student teaching assistant and teacher training and things like that. And one thing that they said is, arrange your room so you don't fall off the stage or trip on a garbage can or something like that. It's always been good advice. Right? So let's just look at some examples, right, of doing this. And these are the 2 case studies that are in the book. I'm going to attach that case study. This particular case study had concerns to it's about the Donner Party, right, that was traveling through the Rocky Mountains in the 1800s and got stranded. There's 45 observations total on 3 variables, and whether they're male, female, and whether they survived or died. This is the notorious one where there's some cannibalism and so on, but they got trapped in the Rocky Mountains, didn't get across the plains in times and the age of the individuals there. So this is trying to predict survival, and try to understand the factors that were males or females more likely to survive. Was there an age effect there as the predictors? The status, 20 survived, 25 died. These are character, right? To put them into a model for R, we need 1s and 0s. And sometimes we'll code things as 1s and 2s or anything else. If we make it numeric, it changes it to 1 and 2, then died and survived. It does it alphabetically. If we subtract 1 from that, it makes it 1, 20, that's the survived one. Right? And so I'm going to create a new variable that's like that. And then I check. Survived is 1 under my new lowercase survived, and died is 0. So I've done a little thing there to change the characters into numeric. And so the command in R is GLM, for generalized linear model. And this is useful, could be used for linear regression, some other regressions. And to do binomial, you tell it what probability distribution family it's in. This Bernoulli is 0, 1, but the more general case is binomial. And I think you can even do like a helper family to see family objects for models. So there's binomial, Gaussian, gamma. There's a bunch of different ones for different things. The default link for binomial is logit. But there are other links that people use for logit, probit, Cauchy, T, and so on, log, complementary log, log. So there are different ones that have done. The one that makes it seems logical to me is the logit. So anyway, when you run this, you tell it, I attach the data set, so you could have a data statement if you hadn't attached it. The survive variable is not actually part of the data set because I kind of created it separately. So that's okay. If I do run the summary, oops, it gives this output. They give some residuals called deviance residuals, which are a little bit different. We can talk about that. But here are the coefficients, 0.69 and male negative 1.38. Right? So that was just the probability of survival among the males, where it's less, that their odds of survival are less. Right? There's a standard error here, a z-value, and it's statistically significant. Right? And that would be the p-value from a normal. Right? There's something called the dispersion parameter, so sometimes things are have extra variation. It doesn't apply to here with just the 0, 1 data, but as we would see after break, so chapter 21 takes up. But what if you had multiple observations at each combination of x's? So you don't only have binomials, you really have a whole bunch of different Bernoullis, you have a bunch of binomials put together. Well, some of them can have larger sample sizes than others, you might have a little extra variation. And instead of doing r squared, it does things in something called deviance, and maybe we'll talk more about that. But it's kind of like AIC for comparing models. It's based on the height of the likelihood. AIC then penalizes if you get more parameters but don't increase the likelihood sufficiently. But anyway, it's significant there. Newton-Raphson Fisher scoring is another variation on that iterative algorithm. So it had to do 4 iterations before it reached some tolerance level to say it was accurate enough. That if it did another one, it wouldn't move. Right? It's close enough to the top. Usually it's not very many. So what else do we get out of this? Just some, that stuff is there. So females, right? So the summary of the model here used male as the predictor. So it was sex, sex, female, male. So female was the default, and then a value of 1 was given for males as the difference from that. So it did it alphabetically. So when male is true, you get a 1. So when it's a female, you don't get this value here. Right? The prediction on the linear scale for the females is 0.6931. Right? That's the prediction for the logit of survival probability for females. So what's the probability of females survived? If you undo that for females, you get a probability of about 66%. In the actual, comparing survivals versus the females, 10 of the 15 survived, which is matches that probability pretty closely. Now, if you're male, right, then the odds are decreased by 1.38. Right? So if you subtract that or multiply those two together, like that, the odds are about 50-50 of survival. That's it's about half. The odds are about half. So that means a probability of about 0.3. So about a third of the men survive. Right? And if you go back to that table, 10 out of 30 is a third. So with just a 0, 1 predictor, it just matches those two categories there with that one parameter. And this was the probability that gave us the p-value for testing that particular one. But there's also age. Here's the histogram of ages. A little bit skewed. I don't know if I would do anything particularly with that because it's not so bad. But you can put age in there as a quantitative variable. Age is a significant predictor. So as people got older, their chance of survival went down. So they kept the younger people alive, or maybe some young people were more able to survive, but once things got hard, some of the older people died off. Right? So to do a prediction, I'm going to create ages 10 to 70 as a little vector here. So my ages little thing there is I'm going to do predictions at all those. The linear prediction takes these coefficients in the model that were down here. There it is. 1.8152 plus ages times this coefficient. So I'm going to do linear predictions. So here's the linear prediction. Right? The linear function there. But I'm going to transform that linear function to the logit scale, right? To the probability scale. And the inverse of that was the e to that, that linear divided by 1 plus that. So let's see what this thing looks like when you do that transformation. You get this. So it's typically a non-linear, usually an S-shaped type of curve for doing that logit. Right? So here's the original data. Right? Ages, survival at 1, died at 0, right? So not much of a little different plot, but that's what it is. There might be some overplotting, so if there's 2 people who died at age 30, they both would be there. So maybe jittering, or once you get large data sets, it's hard to see. There's this little jitter function, right? That adds a little noise there. So yeah, jitters is a little bit more. So you see there is a little bit of overplotting. Right? You can kind of see the density. So why is it a negative effect of age? Right? You're trying to do something that kind of matches this. It kind of ends up being kind of an S shape to match that up. So if we do that, and then I put that predicted plot, right? This is the prediction here. It doesn't really go so near those, but it's getting a much higher probability up here and lower probability down here where there's been more deaths, right? It's influenced by things all along. It has to fit all. You only get 2 coefficients to make this S shape, right? So there's a limit to how much it can go. You just can't pop up, and there are some deaths down here that you'll look. Right? So what if we include sex and age? Should we include that? Should we have an interaction? I'm going to save these 2 models and look at the summary of the first one. So male, still a negative, hurts your chances of survival, and getting older hurts your chances of survival here. You get different standard errors. They're both statistically significant in there, so that seems better. Is there an interaction? That would be the second model. And the second model suggests kind of close. Right? This is, this is one party going through there. So thinking, what are you generalizing to? Other parties getting trapped in the, in the mountains, and maybe there's an interaction. There's not that big of a population, so it's kind of suggestive that maybe there's some effect, but at a 5% significance level wouldn't be significant. ANOVA gives you something. It's not the usual ANOVA. It's this difference of deviances, which are kind of -2 log likelihood values, which are used to compare models generally. AIC would favor the one with the interaction, which is a bigger model. There were 45 individuals, so BIC makes it much more of a toss-up between those 2. What you can look at, if you need to communicate this to somebody, most of the world is not going to be concerned with AIC. They're going to be concerned with predictions and fit and how it looks and accuracy. So if you calculate fitted values for these, so fit 1, our probability of health fitted. I think that there's well, that doesn't tell you too much, but there's fitted and predict. One will give you probabilities, and one does the linear scale. So you just kind of have to pay attention to what you're getting out of it. The fitted can do that. I'm going to do a little manipulation here to make this work out. I'm going to plot the age and survival. I'm going to jitter the ages, because that was kind of nice, wasn't it? To see that a little bit there. So this is males and females. That's on there. So M's for males, females. So there weren't any really older females up to a point making this trip. Now the ages in the data set aren't in order. Right? So if you try to do a line that connects fit versus age, it's just going to bounce all around because the ages aren't just increasing. But this order of the age, if you put that subscript there, it will put it in the order such that the ages are increasing. So you do that. Here's the plots of predictions. Here's the predictions for the males so that they're lower. Here's the predictions for the females. It's higher. Both of them have this. This is the model 1, right? So on the linear scale, the lines are parallel. Right? But on the transform scale, they're different curves. They're not. But you see they're kind of going down. They eventually kind of join up here once you get big, and they would join as you get back up here. But it kind of pictures the different probabilities, right, that are there. The interaction one, I'm going to make these red. So if you have an interaction, the age effect is different in the two. And so the males are just kind of straight across here. They're more flat as that change. The females, it's much lower here, but much more higher survival for the younger females. So on the linear scale, you would see these two lines that are diverging and straight. And on this, it's just two curves that go in different directions a little bit. So the interaction does, seem to start to have some pretty big impact on these estimated probabilities, and maybe you'd want to, use that one. In terms of statistical tests, it's a little toss-up in terms of whether it's significantly better or not. Anyway, so that's what you kind of get out of the logistic regression. The second case study that's in there is a retrospective study where people had either lung cancer or no cancer. These are people who died, I believe. So there's these two things. We need to change it into 1, 0. In this case, I want lung cancer to be 1 and no lung cancer to be 0. So I'll do the transformation just a little bit different. If I do the numerical values, I get 1 and 2, so 2 is no cancer. If I take 2 minus that, now no cancer is 0, and 2 minus 1 is 1. And so I'm going to use this transformation because I want to make it like this. So cancer now is 1, and no cancer is 0. So just change my little transformation a little bit there. This case, had lung cancer, male, socioeconomic status. This was, did these people own a bird or not? So something about having birds and, we don't have that. Year was how many years they smoked. Cigarettes per day was how many cigarettes per day they smoked. These were all smokers. And AG, I'm just trying to recall exactly what that meant. Oh, did I not give? I didn't give out any handouts. Sorry about that. Just wondering. Expecting you to memorize everything. That's right. But the second one is on the second page, so. And so there's 67 of these individuals, these smokers, owned birds, and some did not. Right? And so we're interested in this, owning a bird effect for various reasons. Does this imply is it a direct effect, or is it really a signal for other things about their lifestyle, or something like that? Or are they more concerned with fresh air because they're living with this other animal? Or, I don't know exactly. But if you run one that just has that, there actually is a negative impact on so let's see, one is having cancer, right? And so a negative means you're less likely to get cancer, right? So the people who do not have birds are less likely to get cancer. So the people that do have birds, this would mean would be more likely to get cancer. So there's could be something in the breathing of the dander and everything associated with the birds and the dust and all that makes lung exposure worse, right? So kind of is a secondary exposure, I guess, increasing the chances. Right? So you could, start with some model, or all these different social, female, male, social, economic status, the bird status, years smoking, cigarettes per day, AG, I'm just trying to, age at starting smoking, I think it was an age variable. Right, so if you run that one and run this, right, in this multivariate model, you get the bird effect is still significant. So you're adjusting for some of these other things to kind of make the, it's a retrospective study, so it's the ones with cancer versus not. And if they're different, if the ones with cancer smoke 3 times as much as the other people and smoke 3 times as long, you would say, oh, well, there's obviously a bias in this study because there's these differences. So we put those in the model to try to adjust for the differences through the model. It's imperfect, right? It only can do as much as it can through the equations. So it's not the same as a randomized study. But still, it adjusts some. Years smoking is significant. Having this bird is significant, and that's a negative, that's a bad thing. Right? Social economic says female, male doesn't seem to make a difference in this age started and cigarettes per day. Doesn't seem to make that much of a difference in there. So that's a model. Right? We can do, you can look at individual predictors, maybe taking them out, looking at their impact, and so on. But we're going to do a stepwise selection like we might do for regression. The step function works the same way. I had that family binomial, that was important. I've done a bunch of work and forgotten to put that at the beginning, and then, oh, this is all linear models, okay. But then you need to have that, right? And so the lower model is going to be the one only with bird in it, because we're interested in that hypothesis, so I definitely want that variable in there. And the upper one at this point is going to be that one with all the variables. And what do we get as we step through this? What it does is it goes through and it takes out, taking out any of these 4 variables would make the AIC smaller, and so that would be good. It takes out social economic status, and then it takes out female, male, and then it takes out cigarettes per day, it takes out age started smoking, and it's left with, just the bird thing, and then how many years of smoking. Right? The more years of smoking has a positive impact on the odds, right? So you smoke more, you get more likely to get cancer. That's kind of how you expect. They're highly significant as predictors. We could look at maybe an interaction. Is there an interaction between years and birds? No, that doesn't seem to be significant there. So we come down to this model that, confirms, I think, their suspicion that having a bird pet in a smoky environment with all the, small particles flying around, small particulate matter in the air that they're breathing in along with their cigarette smoke seems to cause cancer more. It's kind of an interesting, hypothesis of how these things work together. At this point, you probably want to do some graphs and things. It's kind of like this, that there's years of smoking and then bird or no bird. So you would get kind of 2 graphs of this without the interaction. Without interaction, it might look more like the blue ones that are kind of going up in kind of a similar fashion. The interaction ones, in this case, in the Donner Party, female, male, kind of cross and show more of a change. So you can do a lot of things with logistic regression. It just requires changing the software a little bit. We'll look at a few variations on this and some binomial data and see what you can do a little bit more in terms of model diagnostics when we come back. But that's after break. So have a nice Thanksgiving and see you after that time.
Hey, Dave. I think I forgot to put the position from one of my references.
That's okay. Don't worry about it. Yeah, that's really fine.
You sure? Like, do I have to?
The position title?
Yeah.
This is the name on it?
Yeah.
The person, yeah. Yeah. Sorry.
Yeah, you too.
Oh, let's see there. Thank you.
Yeah.